Just because we don't know how quantum mechanics work, it doesn't mean we shouldn't know what we are going to be in for. All of us, a revolution in making. Hello friends, and in this video I want to share some fun facts and why we really need quantum computing. Since I've used quite a few examples and analogies to explain quantum concepts, I couldn't keep it short, and hence this video is split into two parts. If this first part excites you, watch part 2 as well, which is part of this playlist, and additional links in the description. Before we talk about quantums, let's do a short time travel. Back in 1969, as part of Apollo 11 mission, we have used computers of that time to send spacecraft to moon, and it was good enough. 5 decades later, we achieved some phenomenal things in the field of science and technology, and now we have some incredible computing power at our disposal. Yet, our current generation supercomputers could not solve many problems of phenomenal scale and magnitude even today. Let's take some case studies where our current generation supercomputers struggle with. Drug discovery. On average, it takes at least 10 years for a new medicine to complete the journey from initial discovery to the marketplace, with clinical trials alone taking almost 6 to 7 years in that. The average cost to research and develop each successful drug is estimated to be roughly $2.6 billion US. What if I say a quantum computer can make the drug discoveries possible in hours instead of decades? What if I say you can have a vaccine for COVID in hours and not have to wait for months together? Let's take another example in the field of material science. If you want to design a material that is as clear as glass but as strong as steel, you have to synthesize several properties one after the other with different combinations and of course with trial and error basis. What if you don't have to synthesize each combination of properties but just simulate them? Today's modern day supercomputers can take billion years to execute such simulations. Energy crisis, the world's third largest problem. But what if I say the electricity can be simply made to circulate around you and can be downloaded when required? No such material exists today to carry electricity of that kind or that nature. But quantum can help discover one with exciting properties like room temperature superconducting materials. The modern digital world runs on the basis of security and cryptography. The most popular method used in cryptography, what you may already know, a public-private key encryption. If you're not familiar, in a very simple term, these two keys are linked mathematically in that a public key can be easily be produced using the private key, but the reverse is extremely difficult. The most simplified version, how some of the most common public-private key encryption work is, you start with 2 prime numbers and each several hundred digits in some cases, and you multiply them together to get a product. The 2 prime numbers are your private key and the product is your public key. Knowing the private key or the 2 prime numbers, it's trivial to reproduce the public key or the product. But knowing only the public key or the product, it's extremely difficult and computationally intensive to determine the correct prime factors of large numbers. This process of prime factorization is so difficult for classical computers that has been relied upon as a security method for decades in popular security technologies such as TLS, RSA, and more recently the Bitcoin blockchain. All 3 of these 3 technologies got a significant portion of everyday internet traffic and transactions. In current scheme of things, hacking an RSA encrypted key is estimated to take billion years, and by the time they break the key, the problem is gone. But what if reversing the public key into a private key wasn't so difficult? Quantum computers can easily do it. Don't get worried about the world of insecure digital world. You should know that there is a new and exciting branch of cryptography called host quantum cryptography. This field is dedicated to providing new ways to secure against both classical and quantum computers. Did you notice a pattern in all of the above-mentioned problems that our classical computer struggles with? Be it financial portfolio management, molecular simulation, integer factorization, they are all optimization problems. How do you optimize your portfolio? How do you optimize factoring integers? Or even how do you optimize the molecular simulations? By the way, whenever I refer to classical computers, my reference is today's phenomenal cloud compute capabilities that can almost power the entire planet. By the way, if you still didn't get your head around the optimization problem, let's take a very simple case study. For example, let's say you have your friends visiting your home, and say 10 of them. They all have to sit around a circular table with 10 chairs around it. How many unique possible combinations you can have them seated? The number 10 may seemingly appear small, but the possible seating arrangements is 10 factorial, which is nothing but 3.6 million possibilities. The interesting fact is, if I just add one more friend to the group, the possible configuration grows exponentially to 40 million combinations, from 3.6 to 40 million possibilities with just one extra member. Do you understand how quickly our supercomputers can run out of compute power on large-scale exponential problems? This is where quantum computing comes in. Quantum computing is not just how small or how fast it is, but it is fundamentally a new way of harnessing nature to do the computation. Quantum computing is the way the nature computes. Take an example of a leaf. It takes light, does some computation magically, and releases oxygen so efficiently. Richard Feynman, a great physicist, was looking at how energy dissipation affects computation. We have got at back of our cortex a few billion neurons, which in turn have trillions and trillions of synaptic charges, which is infinitely small that you could not even light a single watt bulb. But we all know what wonders it can do, isn't it? Feynman said, if we could compute using atoms, an artificial atom that can exhibit characteristics of a real one, we are in for a dramatic change. If you still think quantums are phantoms and would like to discover a little more detail, watch part 2 of this quantum series. Thank you.